Good morning. I would like to begin today's lesson with some little discussion on the notion of Markov process. According to a general point of view on the stochastic process, when we are speaking about a stochastic process in phase space X, that space is a measurable space, B is a sigma algebra of some subsets of X. So according to Kolmogorov's system of axioms, such a process is a function of two arguments, xt omega, that takes on its value in that space X capital, and omega is a point from the space of elementary events. So we have Kolmogorov's triplet omega f p. Omega is the space of all elementary events. F is a sigma algebra of some subsets of omega. The elements of this sigma algebra are called events, and P is a probability measure on F. So P of A is interpreted as the probability of this event. So x of t omega is a stochastic process with its values in x. Here t is interpreted as a time. I will suppose that it is given for all t, or maybe t is in some finite interval. Okay, and this function is such that for any fixed t, this is a random element in that space. This means that the set of all omega from omega capital such that x t omega is a point from a measurable subset of X. This subset of omega is an element of sigma algebra F. In other words, this is an event for any t and for any gamma.
From B. I'm sorry, gamma from B.
Excuse me?
Gamma from B.
Gamma from B. Thank you. Thank you. And for any T, this is an event, and as a rule, we omit this argument, and this event will be written down briefly. X of t is a point from omega. Okay, so for any t, this is an event, and we can say, we can speak about the probability of this event. Okay, this is the notion of a stochastic process or random process. The main characteristic of a stochastic process is given by the following family of measures. Let us consider x to the power n and b n is the product of sigma algebras B n times. Okay, so the joint distribution of the values of our process at the instants of time t1, t2, and so on, tn, we can, this is an event. Okay, I'm sorry. If I take some set from sigma algebra, from this sigma algebra, then, and I fix some instant of time, okay. So we can consider such a system, such a family of probability measures for on this space for all natural, for all integer n that is not less than 1, and for all instants of time t1, t2, tn. Okay, we can define such a family of measures. These measures are called finite dimensional distributions. Two stochastic processes are called stochastically equivalent if their finite dimensional distributions are the same. Okay? So we this Kolmogorov triplet can be chosen in many ways if such a processes have the same finite dimensional distribution. Those processes are called stochastically equivalent. It's like a random variable. The main characteristic of random variable is its distribution, okay? Distribution function. If we know its distribution, we know characteristic functions of that variable and so on. So this is, from the practical point of view, this is the main characteristic of a stochastic process. Okay, and now I would like to remark that it is sufficient to know these finite dimensional distributions for such gamma that are rectangles. Maybe here gamma 0 oh. Okay. Gamma 1, gamma 2, so on, gamma n, where gamma k is a measurable subset of X. If you know these distributions for the sets of this kind, so we can find out the value of this measure for any gamma n from this sigma algebra. Okay, what is a Markov process? So suppose that we have a stochastic process in this space and denote by MS the minimal sigma algebra of events such that it contains all the events of the following kind. R is from 0 to S, including S, and gamma is gamma is a measurable subset of this space. Okay, it is evident that MS is included into MT if S. So the family of sigma algebras MT is called the history of this process. This is the history of the process xt. If we have some other family of sigma algebras, and it turns out that MT is a part of FT for all T, then we say that this process is adapted to this history. This is some more general history, okay? Now, if you have a process, a stochastic process in XB, and suppose that we have two instants of time S and T. S is the present, we consider S as a present instant of time. So here is the past, and here is the future. Okay? From the, if we consider, we can consider x of t as the description of some system that evolves in time. Okay? And it is a stochastic system, so we cannot speak about its state at any instant of time as of something definite. We only can speak about the probability that x of t is in some set, some measurable set in the space. And it is natural to construct prediction of this probability if we know the history up to the instant of time s, up to the present instant of time. We are going to consider the prediction of the state of our system at the future instant of time t. If we know, if we observe the behavior of our system up to the instant of time of present, up to the present instant of time, ms. So it is the best, in some sense, it is the best prediction. Okay, it will be very good to have this prediction. But how to calculate this prediction? It is unclear how to calculate. And Kolmogorov in his paper, I have already cited it here, introduced the following class of systems or stochastic processes. Suppose that our system is such that this prediction is as precise as the following one. The probability that x of t is in gamma if only the state of our system at the present instant of time is given. This is a random variable, and this is a random variable, so this must be held almost surely. And suppose that it is held true for all s less than t, for all gamma from B. If it is so, Kolmogorov called such a process stochastically definite. Stochastically definite. But somewhat later, these processes became to be called Markov processes. Markov.
It would be quite strange if Kolmogorov named them Markov processes.
I will explain right now. Markov processes. He Kolmogorov means that this property is like that for a dynamical system. If we have a dynamical system, suppose that this differential equation has a unique solution for any initial instant of time and any point in phase space. Okay, so this equation determines a dynamical system, okay? And if a dynamical system has the following property: if I know its state at some instant of time tau, if I know, so this state determines the behavior of our system at any time, at any instant of time after tau. Okay?
I'm sorry?
Yeah?
Should this system be autonomous to this condition to be held?
Which one?
I mean, if A depends on T, then it doesn't hold that the future depends only the present.
Right. If I know this coefficient, I can solve for any point, for any initial point. I have solution to any initial instant of time and initial state. Okay? I can solve this equation and I know its behavior at any instant of time after S. Okay?
So the initial condition.
Under some assumptions about this function A, it must be Lipschitz. About Lipschitz, it must satisfy the Lipschitz condition with respect to this. There are, even if the Lipschitz condition does not fulfill, there are some ways to select to construct a dynamical system. One can propose some rule for selecting a unique solution. Maybe there are many solutions, but sometimes it is possible to propose some rule how to choose a unique solution from the set of all solutions. And so such a dynamical system may be defined in the situation when there is many solutions. So in the regular situation, we have such a system that its behavior after the instant of time tau is completely determined by the state of the system at the instant of time tau. This situation is similar to that, you see? But now we have probability, and this property is similar to that, and this is why Kolmogorov call such a system stochastically definite. Stochastically definite. But now the processes with this property are called Markov processes. So I have already mentioned the theorem of Sergei Kuznetsov that theorem asserts that if the space X is not bad, then, and we have a Markov process in that space, then there exists a function of 4 arguments such that it is measurable in X. Here arguments S is less than T, X from X, and gamma from B. So this function is B measurable in this argument. It is a probability measure. Probability measure. On B, and it satisfies the Kolmogorov-Chapman equation. P S X T gamma is equal integral over O X P S X tau Z P tau Z T gamma. There exists in not bad spaces, there exists such a function Psxt gamma that satisfies these 3 conditions, and it is such that this probability is Psx over S T gamma. Almost surely. And how to write down the finite dimensional distributions. for a Markov process. If we have a minimal instant of time, for example 0, so the initial distribution should be given, okay? So we have, besides this function, we have to be given by the distribution at the initial instant of time. This is some measure on X on sigma algebra D. Okay, and now it is very easy using this property. Write down the finite dimensional distribution on the rectangles with these two, with the help of these two objects. Consider the expectation of product indicator function is such that it is equal 1 if x is a point from gamma and equals 0 if x is a point from the complement. Okay, so we fix some instant of time, 0, 0, t1, t2, and so on, tn. And this expectation is exactly the probability that x0 is a point from gamma 0, xt1 is a point from gamma 1, and so on. Okay? So this is exactly finite dimensional distributions on the rectangle. Okay, and how to calculate this? Let us write down it as product of these indicators from 0 to n minus 1 and here write down indicator gamma n of x tn given the history up to the instant of time t n minus 1. Okay, and this is nothing else but this is nothing else but this function at the point t n minus 1 x of t n minus 1 t n gamma n. Okay? And so we now can write down that expectation as the expectation of the product from 0 to n minus 2 indicators gamma k of x tk expectation e gamma n minus 1 x t n minus 1 p p t n minus 1 x t n minus 1 t n gamma n. Given this is a conditional expectation, given the his under the condition that the history up to the instant of time tn minus 2 is fixed. This, let us write down here this way. Okay. N minus 2 okay, and we have some function of xtn minus 1. So it is this expectation can be written as the integral over gamma n minus 1 p t n minus 1 y n minus 1 t n gamma n, and we should integrate it with respect to p t n minus 2 y x of t n minus 2 t n minus 1 d y n minus 1. Okay, and we have some function about depending on x t n minus 2, and here we have indicator function depending on x t n minus 2. So we can continue this chain of equalities, and as a result we can calculate that this distribution, I would like to write down it as the probability that x of 0 is in gamma 0, x of t1 is a point from gamma 1, and so on, x tn is a point from gamma n, is equal to integral gamma 0, the initial distribution, x of t0 dy0, so we integrate with respect to this value, integral over gamma n, p0 y0 t1 dy1, integral over gamma 2 p t1 y1 t2 dy2, and so on, and the final integral, this one is the final integral over gamma n p t n minus 1 y n minus 1 t n d y n. So we have, you see, the finite dimensional distributions are expressed through the transition probability and initial distribution. Now let us make a little break. Let us continue our lesson. So we see that if we have a Markov process, then its finite dimensional distributions are expressed through the transition probability and the initial distribution. And the question arises, is it possible or not to choose the probability, the Kolmogorov's triplet, in such a way that trajectories of the process would be regular functions. What I mean. So we have, suppose that we have some measure, some probability measure, that is initial distribution, and the solution to, some solution to Kolmogorov-Chapman equation. So we can determine all finite dimensional distributions, and it is natural to choose, if it is possible, to choose such a process that its trajectories are regular function. What is trajectory? If I fix omega and consider for fixed omega this function as a function of t, for example, the question may be formulated in the following way. Is it possible, under which conditions on transition probability, maybe this measure, there exists some macro process with these finite dimensional distributions, and such that its trajectories are, for example, continuous functions. There is a theorem that shows that gives some sufficient condition on the transition probability that provide conditions, provide trajectory to be chosen continuous. This theorem was proved by Dynkin in 1952 and independently Keen in 1953. And it says, the theorem says, if X is a complete matrix space and B is the sigma algebra of whatever measurable from space of X, and if the following condition holds true, and if supremum over all x from x, transition probability S x t b epsilon of x. I would like to recall b epsilon of x is the ball of radius epsilon with its center at the point x. C the epsilon x c, the complement to this ball. Okay, so if supremum over all x of this transition probability and supremum over all s less than t less than s plus h less than t. Let us denote this. Expression by alpha epsilon t of h. And our assumption is the following, is as follows. If this function is O small of h as h goes to 0, for fixed epsilon and t. If and if, then there exists a continuous modification of the process x of t. You see, this condition is more strong than the condition in Kolmogorov's definition of a diffusion. Maybe you remember that condition was as follows. This is O small of t minus s for fixed epsilon and fixed x. Okay? And here we have take supremum over all x in our space. Okay? And supremum over each pair of instants of time on a finite interval of time. I will not prove this theorem. It can be found out in many books. For example, the book by Dinkin. And I would like to draw your attention to that fact that diffusion processes that we have constructed satisfy this condition. I would like to recall we have function a s of x and b of s x. This is our d value. This is operator valued.
Sorry?
Yeah.
Does the metric space not need to be separable in this theorem? It works without separability?
As far as I remember, not. This is true for any complete metric space.
Okay, thank you.
So these functions are supposed to be continuous. Continuous and bounded. Bsx is uniformly non-degenerated for all theta from Rd and all Sx okay, and if this function is Hölder continuous in both its arguments s and x, and A is Hölder continuous in the space argument, then there exists fundamental solution to the corresponding parabolic operator, a fundamental solution, and we proved that this function is non-negative, its values are non-negative, the full mass equals 1 identically, and it satisfies the Kolmogorov-Chapman equation. for all s less than tau less than t, x from Rd and y from Rd. So this, therefore it is a transition probability density for a Markov process of a Markov process. Okay, and we have the following, we have had the following estimation on the GSXTY, GSXTY less than a constant t minus s to the power minus d over 2 exp minus mu y minus x square over t minus s with some constants k and mu, positive constants. Okay, and now we can verify that so there exists a Markov process with this transition probability density with respect to Lebesgue measure in Rd, okay? And we can verify that this property is fulfilled for this Markov process. And therefore, there exists a continuous Markov process with this transition probability density. Let us consider this integral. Let us write down these probabilities as the integral over b epsilon x c g s x t y dy. We can write down here k over t minus s to the power d over 2 integral over b epsilon of x c exp minus mu y minus x square t minus s dy. And it can be written, it can be estimated as follows. Let us write down this exponent as the product of two exponents with 1/2 here in each one. And y minus x here is greater than epsilon, okay? So y minus x I replace by epsilon, so I receive k e to the power minus mu epsilon square over t minus s. And here 1/2, okay, 2. Integral over Rd exp minus mu over 2 z square dz. This is a constant. Well, I changed the variable here. I made here this change of variable, so t minus s dy is dz times t minus s to the power d over 2 cancel, so we have, and if I consider s less than t less than s minus plus h, so t minus s is less than h, so if I put here h, I will obtain the estimation, okay? So this is some constant multiplied by e to the power mu epsilon square over 2h. And if h goes to 0, and it is evident that this exponent divided by h goes to 0. Okay? So this condition is fulfilled in our situation. So there exists a continuous Markov process with this transition probability density, and we saw that this is a diffusion in Kolmogorov sense with its drift being given by that function a as x and its diffusion operator being equal to the function b as x. Okay, and now I would like to change the point of view on the Markov process, on the notion of Markov process. You see, the main object in this theory is the transition probability. Okay, the solution to Kolmogorov-Chapman, a solution to Kolmogorov-Chapman equation. So we can treat a Markov process. So suppose that x of t is a Markov process suppose was in RD. In RD. Okay? And B is the sigma algebra of Borel measurable subsets of RD. And denote by P as X T gamma the transition probability of this Markov process. Okay. It is so you remember that the finite dimensional distributions are expressed through the transition probability of this process and an initial distribution and the initial distribution of this process, okay? It is natural to find out such an object that is completely determined by its such an object connected with the Markov process, such that it completely determined by its only its transition probability. And I would like to show how to do it. Let us consider two parametric family of sigma algebra. MST is the minimal sigma algebra containing the following events for all tau from ST and gamma from B. No. Okay. It is natural, not fixed, an initial time, and consider any time, any instant of time as a possible initial instant of time for our process. And on the sigma algebra MS, that is the minimal sigma algebra of events that contains all the sigma algebras MST. If there is a finite instant of time, so this sigma algebra is nothing else but a MST capital. But if tau equals plus infinity, then this sigma algebra is the minimal sigma algebra of events that contains all MST. Okay? The union of these sigma algebras is an algebra, not sigma algebra. So we should generate the minimal sigma algebra generated that algebra, okay, in this case. Okay, so I can define the measure PSX on this sigma algebra MS using the transition probability density. Namely, if A from this sigma algebra has the following form. This is x of T1 is in gamma 1 and so on. X Tn is in gamma n for some n, for some integer n. Okay, then I define this measure as follows. Of A is equal to integral over gamma 1 P S X T1 dy 1 integral over gamma 2 P S X, or excuse me, I'm sorry, P T1 Y1 T2 dy2 and so on, integral over gamma n P T n minus 1 y n minus 1 T n dyn. Okay, and I know this measure on the sets, on the events of this kind, and I can extend this measure on all the sigma algebra MS. Okay, so I have such a family of probabilities measures on MS. We can fix an initial instant of time and fix initial state, initial position, initial location of our process in the phase space. And what is the interpretation of this measure? This is a conditional probability of this event, or more general, of this event, if our process started at the instant of time s, at the point x. Okay? So, what we can say about these measures? P S X of X T the measure of on the probability, this probability of this event is nothing else but P S X T gamma. Okay, and it can be easily verified that the following property is held true for this measures PSX of A given MS tau, where instant of time tau is greater than S, and the event A is from the sigma algebra M tau after tau. It depends on our proofs is after instant of time tau. So it can be easily verified that this is P tau x of tau of A. How to prove this? I would like to give a hint how to prove this. It is sufficient to verify this equality in the case if A is an event of the following kind after tau x of tau 1 belongs to gamma 1 and so on, x of tau n is a point from gamma n, where tau 1 is greater than tau, less than tau 2, and so on, tau n. And let us consider the so A belongs to M tau. Okay? And consider the event B that is defined as follows: x S1 belongs to lambda 1 and so on. X Sm is a point from lambda m, where S1 is greater than S, S2 and so on, Sm. Okay, and Sm is Sm minus 1 and Sm will be equal to tau. Okay, and the gamma k are from B, okay, and lambda j are from B. Okay, so B is an event from MS tau. And you, to verify this equality, you should show that integral over b p s x of a m s tau d p s x is equal integral over b p tau x of tau a d p s x. And it is very easy to verify it because this is nothing else but p s x a b. Okay, and this is a very simple a and b, very simple. You can write down this probability through the transition probability, and it is easy to observe that exactly that expression can be written exactly in this form. Okay, that's all for today. See you next Tuesday. Thank you.